So, dear students, in this video we are going to talk about the property relations across normal shock wave. In the last class we have framed out many governing equations for normal shock. So in this video we are going to manipulate those equations so that important property ratios across normal shock can be derived. The main property ratios across the normal shock wave considered here are T2 by T1, P2 by P1. This is temperature ratio, this is pressure ratio, then density ratio across the shock wave, and also ratio of stagnation pressure across normal shock wave. Sorry. Okay. So here note that this is TP. Okay. Here. Sorry. Okay, so listen here, the subscript 1 represents the upstream quantities and 2 represents the downstream quantities. Okay, so we will think one by one. First we will have an expression for T2 by T1, that is the ratio between the static temperature across the shock. Okay. So for that I am going to rely on the adiabatic energy equation, which is nothing but, I hope that you are familiar with this equation. This is nothing but a manipulated version of adiabatic energy equation. Okay, so now I am going to write this same expression for state 1 and state 2. This is for state 1. And 1 square. This 2 by 2 equal to 1 plus m square. Okay. And we know that as far as the normal shock is concerned, the stagnation temperature remains constant. This is because the stagnation enthalpy must remain constant across a shock wave. Okay. So I can write, instead of T0 2, I can write T0 1. Just because T0 2 equal to T0 2. Okay. Then ultimately I need T2 by T2. Okay. So this is equal to T01 by T1 divided by T02 by T2. Okay. So that means if you simply divide these two equations, what you are going to get is T2 by T1. So this is equal to, simply you divide this expression. What I am going to get is 1 plus gamma minus 1 by 2 m1 square divided by 1 plus gamma minus 1 by 2 square. Okay. So this is the final expression. You have to write down this and you have to remove this. Okay. So we have derived an expression for temperature ratio across shock wave in terms of Mach number. Okay. Now we are going to talk about the pressure ratios P2 by P1 across shock wave. Okay. So for that I am going to rely on continuation. Continuation is ρ1 u1 equal to ρ2 u2. Okay. But what is rho? What is rho? Rho is equal to P by R. Okay, because P is equal to rho R. This is from perfect gas equation. So I can write ρ1 equal to P1 by rho P1 by RT1. Like that, so ρ2 is equal to P2 by RT2. Okay, so now I am going to substitute this values for density. Then I am going to get P1 by RT1 into U1 equal to P2 by RT2 into U2. Now let me manipulate all this equation as follows. That is P1 by root gamma R into root P1 into u1 divided by gamma t1 equal to, similar manipulation can be done here. This is gamma r into root t1 into u2 divided by gamma r t2. Now, can you recognize the quantity within the bracket, both sides? This is nothing but Mach number at T1, because root gamma R1 is equal to A1, the speed of sound at T1. So U1 by A1, that is Mach number at 1. Like that, this is nothing but M2, Mach number corresponding to the state 2. So I can write, and also I can simply cancel this. Okay, so I can write from continuity equation, if you combine with the perfect gas equation, then you can write this P1 by root T1, this is M1 equal to P2 M2 by root T2. Okay, so from this we can write P2 by P1 equal to M1 by M2 into P2 by T1. Okay, or I can write, I can have common root for this. Okay, now this is equal to so P2 by T1 P2 by P1 equal to this M1 by M2 into, what is this? We have already developed the derived the expression for T2 by T1. So we will simply substitute that. This is 1 plus gamma minus 1 by 2 into M1 square divided by, I have split this root here. Okay. This is what we have already developed. So I can, okay, so this is the expression for pressure ratio across the normal shock wave. Okay, so here we have derived this expression, pressure ratio, with the help of, I would say, with the help of continuity equation, perfect gas equation, and also we have rely on the adiabatic energy equation, because this is nothing but the essence of this expression is the essence of adiabatic energy. So we have used everything, but we haven't touched the moment equation. Okay, now I am going to develop another expression for T2 by T1. In this time it is from the moment equation. Okay, so this you have to write down and you have to remember. So we are going to have another expression for T2 by T1. In this time we are going to rely on moment equation. So what is moment equation? Moment equation is P1 plus rho1 u1 square equal to P2 plus rho2 u2 square. Okay, now let me take P1 outside. So this is rho1 u1 square by P1 equal to, here also we will take P2 outside, 1 plus rho2 u2 square by P2. Okay, now we will listen to this quantity rho u square by P. What is this quantity? I can write what is rho by P. We know that P is equal to rho R. So rho by P is equal to 1 by R, isn't it? Okay, then I can write this u square by RT. Okay, now I will add gamma on both sides. That is equal to u square by gamma RT. So what is gamma RT? Gamma RT is the square of velocity of sound. That means it's equal to gamma u square by a square. Okay, so this is equal to gamma m square. So this quantity is gamma m square. So So now I will substitute. So that means P1 equal to, P1 equal to 1 plus rho 1. Instead of this quantity, I can write gamma m1 square because this is corresponding to the state 1. Okay, equal to P2 1 plus gamma 2 square. So we can simply manipulate this equation, and finally you can write. Finally I can write P2 by P1, okay, equal to 1 plus gamma m1 square divided by 1 plus gamma m2. So this is also acceptable. So we have developed two expressions for pressure ratio. Both are acceptable, equally acceptable. So write down and you have to remember this. Okay. Now we are going to talk about the density ratio. Density ratio. So let me erase all this. Density ratio, that is rho 2 by rho 1. Okay, it's very simple because you know that P is equal to gamma RT. Rho RT. So that means rho is equal to P by RT. So it means that rho 2 by rho 1 equal to P2 by RT2 divided by P1 by RT1. So that means simplifies that rho 2 by rho 1 equal to P2 by P1 into T1 by T2. Okay. So now we have already developed the expression for pressure ratio and temperature ratio. So we will simply substitute this. So P2 by P1, you have two relations. I will simply use one. You can, if you can use another. This is the moment equation, or you can use another equation. And we have already derived the expression of T2 by T1. Here it is T1 by T2. So simply you will split it. That means this plus gamma minus 2 by 2 and 2 square divided by so this is the expression for density ratio in terms of Mach number. Okay, so all of this are in terms of, all the ratios are in terms of Mach numbers. Okay. Now another ratio, property ratio, which are of great interest in shock analysis is ratio of stagnation pressures across the normal shock wave. Okay. So how will you get it? This. So this is equal to, we have a small trick here. This is equal to P02 by P2 into P2 by P01 into P01 divided by P1. So I have viewed this ratio as a product of three important ratios, and I'm sorry, P1, sorry. Okay, now it's okay. Now P2 cancels and P1 cancels. So finally we get P02 and P0. Okay. We have already calculated this. We have two expressions for it. We can use anything. But how will you get this to? see, the first and the last ratio is a connection between the stagnation pressure to its corresponding stagnation pressure. Okay, stagnation from the static quantity to the stagnation pressure. Static quantity to the stagnation condition. Okay, so you handle those equations. We know that P0 by P equal to, in terms of the corresponding temperature, raised to gamma by gamma minus 1, because when we move from the static state to the stagnation state, we have to follow a isentropic relation. So this is what it means. So then I can write equal to, so this is about the state 2. So that means this is equal to 0 by T2 raised to gamma by gamma minus 1. This is 1 plus gamma m1 square by 1 plus gamma m2 square into, what is this? See, here it is P0 2 by P2, here it is P1 by P0. Okay, so I can write P0 1 by P. Sorry. So this expression is P0 by P raised to minus 1 by 1. So what is this quantity? This is nothing but 1 plus gamma minus 1 by 2 m2 raised to gamma by gamma minus 1 into 1 plus gamma m1 square divided by 1 plus gamma m2 square, and this is 1 plus gamma minus 1 by 2 m1 square raised to minus gamma by, okay. Here I have developed an expression for the density ratio. Sorry, this is not density ratio, this is okay. So we are going to conclude. Here we have developed the main important property ratios across the normal shock wave in terms of the Mach numbers, because all of this ratio is a function of m1 and m2 for a given gamma, for a given medium. Okay, so we will continue this discussion in the next video also, where we are going to develop a relationship between the Mach numbers. Okay, so far we might have feel that all of this ratio is a function of m1 and m2. Okay, but in the next class we will have a relation between m1 and m2. Okay, so this is where we are going to proceed. So it is too long, so we will cut here. So we will see you in the next class. Okay, thank you for watching.